Good afternoon to everybody. It's a pleasure to introduce this VOSTAR webinar organized by Mectron company. The aim of this webinar is to present the VOSTAR. It's a new word. It means a new AR wearable head-mounted display recently developed in European countries as an advanced navigation tool for maxillofacial surgery and for other non-endoscopic surgeries. Our aim is in this webinar is to report results of in vivo and in vitro tests with VOSTARs to evaluate its feasibility and accuracy. We will have two speakers who were engaged in the last 3 years in this project, and we hope that with the webinar will be for everybody a great opportunity to learn more about augmented reality. Augmented reality in maxillofacial surgery is one of the most interesting and fascinating area to discuss indication and tip and tricks directly with the expert in maxillofacial area. First speaker will be the Professor of Engineering Vincenzo Ferrari from the University of Pisa. His topic has the title, How and Why VOSTARs Permits an Accurate Augmented Reality Surgical Guidance. Please, Vincenzo, it's up to you.
May I suggest that during the presentation, the camera and the mics are switched off. Any question can be typed in the chat, and then at the end of the presentation, we are going to read the question and answer them. Thank you very much.
Thank you very much, Renato, for your outline about the technical aspects, and many thanks to the Professor Marchetti for the introduction. So I will start with a quick introduction about augmented reality from an engineering point of view, and then I will describe the technical results of the H2020 VOSTARs project that I am coordinating with the honor and pleasure. We are in the context of computer-assisted surgery, and my group in Pisa work in this field since 2006, covering planning, surgical simulation, and also surgical navigation using mainly augmented reality. We are engineers. We are inside the hospital of Pisa, and the close distance with the surgeons allow us to have a strong collaboration with the surgeons. But we collaborate also with the other groups outside our hospital, and mainly with the group of Professor Marchetti in Bologna. The story about augmented reality in medicine starts about in 1994, and in 1994 Professor Crimson at MIT showed the possibility to merge a real view of the patient with the virtual information coming from MRI images. After that, there was a bit of interest, and in particular, in the last years, we have an explosion of the interest confirmed by the number of publications in this field, mainly due to the maturity of some technologies in terms of computational unity and displays. Talking about augmented reality in surgery, it is important to outline that we can offer just a sort of X-ray vision. The real X-ray vision is only for Superman. What we can offer to the surgeon is just a sort of virtual X-ray vision. What we can do is to obtain a precise geometrical information about the patient, and this information can be obtained through preoperative images, volumetric images as CT or MRI. And then if you are able to align this information with the patient, we can guide the surgical procedure. The approach is the same as in a traditional surgical navigator without an augmented reality information, because also in the image-based surgical navigator, the input comes from preoperative volumetric image. In case of augmented reality, we have a different visualization modality. For this reason, given the 7 aspects related to the development of an augmented reality system for surgery, the first 4 points are the same that we have to take into account also in case of a traditional surgical navigator without augmented reality. While in case of an augmented reality visualization, we have more points to take into account. At first, the visualization. Regarding the visualization, we can obtain just an overlay between real and virtual, as in these cases, but this simple visualization is not so useful in many kind of intervention. And what we understood is that for every kind of intervention, we have to design and implement a specific visualization modality taking into account the surgeon needs. For example, with the system that we developed in 2014, based on a virtual reality visor with a couple of cameras in front, and we used the cameras to offer the real view to the user and also to perform tracking without any external tracking devices. So, using this system with the group of Professor Marchetti and Dr. Badiali, we tried to use augmented reality to guide the repositioning of bone fragment, a common task in their surgery. So the surgeon, before surgery, can optimally plan the pose to obtain in the patient, and our goal was to guide with augmented reality this repositioning. We started with the traditional overlay, but as you can see, also using the transparency, it's impossible to understand if the alignment is obtained or not, because we have an occlusion between real and virtual objects. So in this case, given that every patient wear the brackets of the orthodontic implants that you can see in this mannequin represented as black dots, we can guide the alignment given some virtual crosses, and if the user, the surgeon, is able to align real brackets with virtual crosses, the alignment is guaranteed based on geometric rules related to projective geometries. And the same approach can be used also to guide other alignment of other bone fragments. Furthermore, we have to take into account the display type that we can select that determines also the perception location. It is well known that in case of endoscopic surgery, the most ergonomic solution is the using of a standard stand-up display, as during endoscopic intervention without augmented reality. We can also use the projector and the patient as a screen. We started and we understood that it can be useful also the projector, but we have to investigate more. While the using of augmented reality glasses for open and surface surgery is the current hot topic around the world. And in this regard, the availability of very powerful augmented reality glasses, for example, the HoloLens that you can see here, pushed the development of a lot of prototypes around the world. If you look in Google, you can find a lot of examples related to the using of the HoloLens, but also of other visors for surgery. But the using of traditional and general purpose visors to guide surgery can introduce some troubles. And to understand such troubles, we have to learn a bit about the approaches to implement an augmented reality glass. The HoloLens, as the Google Glass, implemented the optical see-through modality in which we have a semi-transparent display in front of the user, and on this semi-transparent display we can add virtual information in the form of a 2D image for each eye. This display offers the comfort of a natural view through the semi-transparent display, but given that the virtual information is optically projected at a certain distance in front of the user, if this distance doesn't match the real distance of the object, we can have a discomfort due to focus troubles. That means that the user is not able to obtain an in-focus image at the same time of both virtual and real. For example, given the Microsoft HoloLens specification, in the HoloLens, the virtual information is projected at 2 meters. And Microsoft, given the depth of focus of the human eyes, declared as the comfort zone for the HoloLens a range of distances that start at 1 meter. But in case of surgery, obviously, the patient is closer than 1 meter to the eye. And so we tried to understand if, even if without the comfort of an image, a virtual image in focus with the real one, it is possible or not to perform an augmented reality guidance in case of manual precision tasks. To do this, we implemented a very simple study showing in front of the user over a white sheet some virtual dots, asking the user to connect the dots with a pen. And the results were, in many cases, in images like this one with very huge errors in terms of distances and terms also of topology, demonstrating that it's impossible using a focus plane at 2 meters as in the HoloLens to guide a manual precision task. Why? Because the user cannot obtain in focus at the same time real and virtual at the same time. If I try to obtain in focus the virtual dot, the real world is out of focus and vice versa. But in case of an optical see-through device, we have another problem. It is related to the parallax effect that introduces an alignment error between real and virtual, and it is related to the position of the eye in respect to the display. Given that today it's impossible to precisely determine in a robust way the position of the eye in respect to the display, today with the optical see-through approach, we have a misalignment due to the parallax, as declared by Microsoft, that declared an error in terms of angular error. That means an error of about 5 millimeters at 50 centimeters. So using an optical see-through device means that over the patient on the surgical bed, we have a registration error of the guidance of about 5 millimeters. Too huge in many cases of surgeries. During the VOSTARS project, we understood how to solve such kind of problem also in case of optical see-through devices. 2 publications just accepted demonstrate this possibility, but we only developed feasibility studies. The technology is not ready. So, if we need an accurate registration, we have to switch to the video see-through modality. The video see-through modality means the using of a traditional display, not transparent, the using of the camera to acquire the images coming from the real environment. And if you are able to align the virtual information on the camera images, the alignment, the registration is maintained even if the eye moves in respect to the display. So we remove the parallax using this approach. But we have to work with the camera mediated view. So both the approaches offer pros and cons. Mainly the optical see-through approach offers the comfort and the video see-through approach offers the accuracy. And this is the base idea of VOSTARS. In VOSTARS, the idea is to offer a device able to switch between VST and OST modality. And today, after 4 years of work, thanks to the founding of the European Commission, we developed and tested in the surgical room, as Dr. Badiali will show later, the first hybrid optical and video see-through system that, given the hybrid nature, is able to offer an accurate augmented reality guidance over a wearable device. How we can switch between optical and video see-through? The device is composed by a waveguide, a semi-transparent waveguide, so the system can work in optical see-through. But thanks to a couple of cameras and thanks to an optical shutter based on an LCD panel, when the user decides to switch in video see-through, we can close the LCD panel and turn on the cameras to show the user the real environment acquired by the cameras. In this video that you can download from our website, you can see the system at work. The surgeon can use the system, can wear the system to prepare the patient, so he can perform some steps of the intervention in optical see-through modality. In the optical see-through modality, we can add information not strictly related to the patient from a geometrical point of view, as for example, the information from the anesthesia devices. And when the surgical guidance is required, the system can switch in video see-through. And as you can see here, we can add virtual information. As you can see, virtual and real is maintained aligned even if we have a movement of both real and virtual due to the natural movement of the head. In particular, in this case, the tracking is obtained tracking this patient-specific template anchored with the teeth of the patient. Regarding the accuracy, we performed some tests, and we can guarantee an error lower than 1 millimeter. For example, in the tracing of a cutting line. Less than 1 millimeter, not on the eye, but directly on the hand of the user, because we performed a manual task test. This is the final prototype that we developed. It's not a rendering, it is the real job object that we developed and also really tested. We developed this system thanks to the entire consortium composed by industrial partners and also academic institutions. Before to conclude, a special thanks to my group, most of them in this picture. Thank you very much for your attention, and now it's time to see the system at work in the surgical room, and so I ask the switching to Dr. Badiali.
Okay, can you hear me?
Yes.
Yes, very well.
Very good.
Yes, okay.
Good evening, everybody, and thank you for being here. The purpose of my lecture is threefold. The first is to explain why augmented reality could be an important improvement for surgery, according to our point of view. The second is to show you the method and results of the clinical trial aimed to validate the VOSTARS system. And the last is to show you the potential future evolutions of this device and more in general of augmented reality for surgery. So let's start with a very simple question. What would a surgeon want from AR? The answer is in our daily routine. Surgeons always wanted to display deep anatomy when approaching to a patient, or even better, their surgical plan. So a very understandable aim of augmented reality could be to let the surgeon have the full view on deep anatomy, but in a 3D environment. Someone could say that navigation systems do the same, but probably they are quite similar to the standard navigation system of our car, which forces us to take eyes away from the street in order to have the necessary information on about the pathway. Everybody experienced that this could lead to some sort of mismatch between virtuality and reality. On the other side, AR could help surgeon to bring the sight back to the patient, just like it helps bringing pathway information right onto the street when we drive, or at least this is what the future could bring us. But what kind of information? To start, anatomy, topographic anatomy, like bones, nerves, vessels, but also pathology location and boundaries. Osteotomy cuts or trajectories for tool insertion. Repositioning of a bone segment, as we already saw in Vincenzo's presentation, but also positioning of an implant, which is something routinely helpful. And last, AR could help us to realize minimally invasive non-endoscopic surgery, showing to surgeons areas which are excluded to their sight. So in one simple sentence, AR could help to see through the body. And in particular, this device could do it in two ways at the same time. This is why it's called hybrid. The first is optical see-through, and the second one is video see-through. So let's see in depth. In video see-through, the patient is recorded by cameras and the surgeon sees in a visor what the cameras grab, plus the virtual content. While in optical see-through, the virtual content is projected on a transparent glass. Vincenzo Ferrari already told us technical and perceptual pros and cons of both approaches. Of course, from the surgeon's point of view, optical see-through is much more natural and ergonomic, but as far as it's not accurate like video see-through, we should use this glass for high accuracy demanding tasks, saving optical see-through for all the others. You also already seen how the trial prototype looks like. It could be considered uglier than the design one, but it worked, and that's what matters. Again, Vincenzo already told us the technical specification. The clinical trial was then ready to start. The University of Bologna was leading this work package, but the clinical units involved were three. Of course, maxillofacial surgery in Bologna at the St. Ursula University Hospital, then neurosurgery from the Charité Hospital in Berlin, led by Professor Ulrich Tomale, and ENT surgery from the St. Gertrauden Hospital in Berlin, led by Professor Oliver Kaschke and Dr. Jan. The trial was organized in two phases. A first in vitro preclinical test on phantom, and after that, the in vivo testing. Bologna was involved in interventional investigation about that. So let's start from in vitro tests. We built a 3D printed phantom following a real patient anatomy, and we performed the tests on it. In this video, you can see several AR modalities. You've already seen some of them. We asked ourselves what was the ideal task to be tested on the device. To be honest, we already defined it during the project writing, but of course, now that we had our tool, we could be much more appropriate in the selection. And so, for example, vessels, soft tissue, parotid, tumors. What we chose in the end was maxillary left 1. Why then? The reason is twofold. The first is it is a very safe procedure, and it's really standard and repeatable. And there is a third reason. Level 1 osteotomy was the task we already investigated in 2014, as Vincenzo already said, using our first augmented reality system. So we already had data to be compared. Then we started the testing in the operating room environment in order to assess the system feasibility in real surgical conditions, and the outcome was really satisfactory. You can see here how the guidance is displayed on bone, on maxillary bone, and the good lining condition in the operating room. The saw can follow the line so that achieving the correct pathway of the osteotomy. And in the last part of the video, you can see the line superimposed with the cut. So in order to perform the task multiple times without throwing away a phantom every time, we traced the osteotomy with a marker instead of performing a real cut. Then we measured the accuracy with a guide with different tolerance. As you see, 100% of lines were traced with a tolerance of 1 millimeter, more than 95% with a tolerance of 0.75 millimeters, and almost 88% with a tolerance of 0.5 millimeter. We considered these results satisfactory and we proceeded. And we started the in vivo tests. Of course, we had to fulfill all the ethical requirements for using a non-CE marked device on a real patient, which also included electrical safety tests and electromagnetic compatibility tests. And finally, we got into the operating room and performed the first surgery. Here you can see how augmented reality looks like for the operator. Both sides of the patients are displayed for both eyes of the surgeon. Colors in the video are a bit red shifted because the signal from the display is sent to the computer with some chromatic distortion, but the surgeon receives a much more natural view, but of course it's in his eyes and not recordable. So you can clearly see that the modality of visualization VOR is clear and allows the surgeon to follow the pathway quite easily. The study group is composed by 7 patients so far, with a good balance between males and females and class 2 and 3. Of course, as we already said, all procedures were level 1. Now I want to give you the chance to experience, to try the experience to be with us inside the OR. Of course, the COVID pandemic was a great challenge and stopped our testing during spring, but we went on. And this video was recorded during the last intervention. And you can see every step of the procedure. This is the tracker, which is leaf-based. Of course, when you first wear the visor, you have to adapt a little bit, but then you can easily proceed to the surgical task. And everybody can see what you are seeing from the monitors in the OR. Okay, let's go to the results. To assess the accuracy of the procedure, we could use the postoperative CT scan, but we didn't, because bone modifications and artifacts could give an accurate superimposition. So the method we chose was similar to the phantom test, a guide with a teeth-based reference and a slot of 1.5 millimeters, which means 0.5 millimeters plus and minus a cut, which is 1 millimeter narrow. We then estimated the percentage of the cut visible inside the slot. And these are the results. Among the 7 patients, we had a mean of 93% of osteotomy inside the 1.5 millimeter interval of, for the right side, and 79 for the left side. The median was 100% for both sides. Task execution times were good, between 2.7 and 3.1 minutes among sides, with a median of 3 minutes. No significant complication occurred except one hematoma, which we judge not related to the procedure but to the patient comorbidities. And all postoperative outcomes were satisfactory. So in conclusion of the work package 9, we can say that the VOSTAR system showed a good usability in the operating room, and also a satisfactory accuracy in surgical reproduction of the preoperative plan, which was the primary endpoint of the project, and also acceptable times in task execution, which was the secondary endpoint. So what's next? In our perspective, we have several goals we should aim in the next future. Some of them are already coming, some other needs more effort, but we are working on it. The first is to use the definitive system. And as Vincenzo showed you before, it's already here. We tried it, we tested it, and results, of course, we tested it in vitro environment. Results are good and comparable to the other prototype. Then, of course, we should develop new features, new visualization modalities, like, for example, the positioning guidance. For this task, we already developed some visualization modalities that are potentially useful, like this grid, which has the benefit to be usable also in optical see-through modality. And you can see that if the grids match, then the position is correct. Another obvious goal is to move from a safe procedure like level 1 to more complex procedure, osteotomies, but also soft tissue. And eventually to realize that paradigm of minimal invasive non-endoscopic surgery, eventually using approaches, surgical approaches, which can be far smaller than the one displayed in the picture. Then we have to move from head and neck to the whole body. And about this topic, we already developed some good applications, thanks to the effort of a large group of research, in particular my colleague Achille Tersitano and the engineers led by Professor Manuela Marcelli. As you can see here, could be used for fibular free flap harvesting. We already investigated the feasibility of this task and results were satisfactory. So this kind of application can be implemented in the VOSTARS device. And to conclude, a promising goal is, of course, education and training. About this, we are developing a very interesting application thanks to the collaboration with our anatomy department led by Professor Lucia Manzi. This application is made for anatomy learning and can be applied to physical models or cadavers. And we hope giving to the operator a very augmented experience in learning anatomy or surgical procedures. So let me conclude. Thank you for the kind attention, and I really want to stress that the power of observation is something that every surgeon could aim. Thank you very much.
So Giovanni, many compliments for your part of the presentation. I think that we can start with the answer.
Yes, there are questions. I'm gonna read the questions, and thank you, Vincenzo. Thank you, Giovanni. I'm reading the question, and you are, of course, asked to answer the question. The first question from Dr. Roberto Magherini. The question is, how much time is spent in the registration of the patient with the markers?
Yeah, I can answer to this question. I also wrote something in the chat about this question. For this particular intervention, we used a template-based registration. That means that we design for every patient a template with the markers attached, starting from preoperative images of the patient. So in the surgical room, the surgeon has only to fix this template on the teeth of the patient, because the registration is guaranteed by the matching of the template with the teeth, without any point-based or surface-based registration approach. Obviously, the surgeon has to maintain the template during the procedure anchored with the teeth. Giovanni, would you like to add something about this?
Yes, of course. This kind of registration applies quite well to every procedure which is performed on the maxillary bone. But of course, if we want to exploit and spread the usability of the system to other anatomical areas, we will have to design a specific kind of registration, probably a point-based or surface-based registration for areas which are far from the teeth. A similar approach could be used for the mandible, of course, using the lower dental arch. And yes, the tracker, which is this, should be secured to the teeth. Of course, you can also fix it, in particular when you have an orthodontic patient, you can fix it to the braces. So it's quite easy to have a stable and correct registration.
Giovanni, Giovanni De Rosa asked if the marker moves. Can you answer him?
If I correctly understand the question, how do I understand that the marker is moved and the registration is not anymore accurate? Okay. We added, and in some videos you could see it, we added some anatomical references, for example, the braces of orthodontic appliance, or the arches of the gum, or other anatomical fixed structures that you can use anytime to assess if your registration is still correct. Of course, this doesn't apply to the parts that you are moving and are not connected to the registration tool. But for every anatomical parts connected to the registration tool, these informations are enough to let you check if you are registered or not.
Giovanni, if you are able to show us one more time in the part of your presentation about this aspect, we can highlight that the using of augmented reality in respect to the traditional navigator can allow the user and the entire surgical team to highlight, to understand if the marker is moved or not. While in case of traditional navigator, in case of movement, we can have additional troubles.
In this case, which was the first, we used a virtual reproduction of the teeth and braces. So as you can see in the two videos, can you see the video? Can you confirm?
Yeah.
Okay, perfect. And then you see that the yellow teeth and brackets are correctly matching to the real one. So if you see that those are moving, then you understand that the registration is not anymore correct. But to be with the project going on, we developed different ways to check this, because of course those images can be easily, let's say, can be affected by the parallax error. So, for example, you can see here in this image the arches of the gum. Here. Do you see it? Vincenzo is.
Yeah.
Okay, perfect.
Yes.
So in this way, we could check if the registration was correct using this specific anatomic design of the gum, which was here. You see it here, the teeth and also the arches of the gum. Did I answer your question?
Okay, there are more questions. The next one is from Dr. Roberto Piazza. The question is the system standalone or not?
Vincenzo, who answers?
Yeah, I can answer. Yes, the system is based just on the visor connected with the flexible cable with an external PC. So the system is not completely wearable. So on the system, we don't have the battery and the computational unit, because we preferred to use a wired solution to reduce the weight and the heat over the head of the surgeon, and at the same time to have the possibility to have more computational power. And we understood, and Giovanni can confirm, that the cable that connects the visor with the external computer doesn't impact on the logistics around the surgical table.
If I may add a comment, maybe the question was addressed to the fact that navigation system have cameras, infrared cameras, which are somewhere on around the surgical field. In this case, the answer to the question is yes. The system is standalone, because you just have to wear the helmet, the head-mounted display, and to look to the surgical field with it. So no other external camera is needed to register the patient, to track the patient.
And the next question is, how does preparation from Marco Tricate, sorry. How does preparation for the surgery work? Is it 3D scan, or, I mean, what is it? What is it required? Actually, Vincenzo has already answered in the chat, but this is a question for everybody. The answer is for everybody, so please. It
sounds like a very large question. I don't understand if the colleague asks about the surgical preparation or the preparation, the virtual planning. Dr.
Tricate, you can unmute and ask the question yourself.
Anyway, the patient is, of course, we perform virtual surgery using a 3D model with the patient obtained by the CT scan and 3D scan of the dental arches, using available softwares for virtual planning in orthodontic surgery. But of course, this is according to the procedure that we selected. So if the procedure will change, of course, we will have to use other potential ways to prepare the surgery. And then we just export this information and load the information on the augmented reality system in order to visualize it. If the question is asking the preparation to the surgery, in many of these surgeries, let's say we've been prepared performing the surgery on the phantom the day before in order to be perfectly, let's say, working the next day during surgery.
Yes, thank you. I think you have answered my question. Thank you.
Okay. The next question is from Marina Carbone. What about the resolution and field of view of the visor, also in respect to the competitors?
I think Vincenzo could answer.
Okay, it's a question for me. Okay. At the beginning of the project, we worked a lot to understand the choice in terms of angle of view and resolution. Asking to many surgeons and also to Giovanni, the answer was okay, we need a very huge resolution and a very huge angle of view. But from a technological point of view, it's impossible today. We cannot offer too much resolution on a huge angle of view. And furthermore, increasing too much the angle of view determines of an increasing of the optics and so on the total weight of the system. After that, we understood that given the distances between the surgeon and the patient, and given the dimension of the patient with simple geometrical rules, we understood that 30 degrees in the angle of view are NO. And so 80 or 90 degrees as in virtual reality visors are not required. Regarding the resolution, we have to take into account not the absolute resolution in pixel, but we have to calculate the angular resolution required to perform surgery. That means how many pixels I need for each degree. And the answer comes from our physiology. We have a limit in terms of angular resolution of our eyes that means about 60 points per degree. And so we obtained a trade-off between the surgical needs, the physiological needs, and the technology, taking into account an angle of view of about 30 degrees, offering 50, 60 pixels per degree. That means on the horizontal the direction 1280 pixels. So our current resolution is 1280 pixels by 720 on the vertical direction on a 30 on an angle of view of 30 degrees. This allows to offer the NO angle of view and an NO angular resolution.
Thank you. The next question is from Dr. Salvatore Battaglia. Dr. Battaglia congratulates to the speakers for the presentation. The question is, do you think that this type of registration would overcome the problem of navigation when performing surgery to a movable bone such as mandible and jaw?
I'm trying to read the question with you. Anyway, the the answer is yes, of course. This kind of tracking using teeth allows to navigate much more easily the mandible. But of course, this is just for the mandible. If you have to track other movable segments, or at least a bone segment that you have cut and you want to reposition, then of course I think we have to design specific tools to track bone segments which are different from the jaws, because the jaws have the dental arches, but other bone segments don't. So the answer is yes, but it's linked to the kind of segment that you want to track.
Thank you. The next question is from Dr. Joseph Muhammad. In your study, was a single operator doing the surgery? How long would it take to acquire the skills to work surgically in augmented reality? How can you assess the depth of the bone cut with augmented reality? It is actually 3 questions in one.
Okay, so yes, the operator was me every time. So was a single operator testing. And how long? I don't know. I mean, the task that we experienced was relatively simple, and I explained you the reason why. So I would say that we made some testing on the phantom, so in vitro environment, before getting onto the real patient, but they were not so long. I think that it really depends on the surgical task you are going to perform with augmented reality. So what of course, I imagine for the future of this kind of technology is that the surgeon could train on the specific task before going into the OR until he has reached a very good point of the learning curve. And about the third question, the depth is not visualized, at least was not visualized in our testing. So it was assessed just clinically. Of course, one way to track the depth is to track also the saw, the surgical saw. So if you track the piezoelectric saw, for example, you can see where the tip is compared to the patient, and this way you have a good assessment of the depth. But it's one of the features that we still have to develop.
Thank you, Dr. Badiali. The next question is from Giovanni De Rosa. It's clear the problem's resolution about registration in VST system, video see-through, but it's not more complicated to operate it with ends without depth or the real distance from real scene with this technology?
Well, the VST visualization modality is fairly one-to-one to the real environment. And the visor is stereoscopic. So it's not true that depth is not perceived. Depth is perceived, and the real distance is, say, there is a slight mismatch in terms of speed of the movement, probably, but from the visual point of view, the visor is shows you a very correct experience of the 3D real environment.
Thank you very much.
Giovanni, I would like to add something about this point, given it seems to be the last. We are at the end. Regarding the depth perception, as told by Giovanni, the match between the camera and the display is set to be 1:1. But given that the cameras are a bit in front of the eyes, the point of view of the camera is a bit different in respect to the natural point of view of the eye. It means that we can set a perfect one-to-one correspondence only at the prefixed distance. Given the specific user, we can change this distance. When the objects are not exactly at this distance, we have a bit of difference in respect to the natural view, but we performed a perceptual study, and we demonstrated that even if the camera is not exactly at the eye position, the user is in any case able to understand the differences of depth with the inaccuracy of less than 1 millimeter also in depth.
There is the last question, again from Dr. Muhammad. Do you feel that there is a difference in working with piezosurgery tips for augmented reality than conventional rotary instrument? Be careful. But who's going to answer?
Well, we didn't think about using rotating instruments because we had to select a tool with the, let's say, the most fixed tip possible. And among saws, surgical saws, the piezosurgery was perfect for the task. Probably it's possible to use the augmented reality also with standard saws or rotating tools. What I can say is that I have to, let's say, talk about a shortcoming of the VST modality, which can be a little bit confused when there is a lot of drops of the irrigation. Probably a rotating instrument would cause a much more, a greater cloud of water drops, and making the image less clear. But as far as we tested only piezosurgery, I cannot say something about something very consistent about rotating instruments, but I can imagine that it's possible.
And one more question is, in addition to the accuracy and precision, which are the other advantages and which are the disadvantages of the system for both surgeons and patients?
Well, I think that accuracy and precision are for sure advantages both for the surgeon and the patient. As you saw from the results, we had no significant loss of time. And I can imagine then when the learning curve is complete for specific tasks, for certain tasks, this kind of technology could speed up the process, because of course it's an improved navigation. And I think these are the greatest benefit for both the surgeon and the patient: accuracy and time and sparing time.
Actually, there is a lot of interest. We are getting questions, more and more questions. Again, one from Dr. Muhammad. Do you feel that the surgery with augmented reality will support the use of robotic surgery in the future?
Giovanni, I can answer to this question. The answer is it depends, because if you are talking about endoscopic robotic surgery, like the Da Vinci robot, we already have some examples of augmented reality view on the DaVinci display. But for an engineer, it's exactly the case of a traditional endoscopic surgery, with or without the robot. We have just to superimpose the augmented reality view on the camera images. So in this case, the trouble can be if we are using the robot on soft tissues instead of rigid bones. And in this case, we have to work with the more sophisticated registration modality that are not mature at this time, or eventually using additional real-time volumetric images as 3D ultrasound probes. While if we are talking about other robots, for example, for orthopedic surgery, in such case, the winning approach seems to be cooperative robots. So, for example, a robot that allow the surgeon to obtain the right alignment of the reamer, and then the robot collaborates with the surgeon. In this case, the availability of an augmented reality visor can be an improvement because the surgeon can be guided both by the robot and also by the augmented reality. Finally, in case of a completely automatic robot, for example, to perform the cutting or the reaming of a bone, the augmented reality visor can be used to verify the right alignment and the registration at the beginning, and then during the procedure to verify that the registration is maintained.
Thank you. We have a question from Dr. Blanca Alejos. Does the visor allow the adjustment of the transparency of the augmented reality elements visualized?
In case the transparencies can be adjusted with the software. Yes, the transparency can be adjusted through the software also in real time.
In real time, you said?
Yeah.
Okay. And then we have a question from Federico Pedrocchi. Federico Pedrocchi is a journalist who deals with science. And the question is, surgery is also an activity that obviously includes making mistakes. What are the mistakes that you think it will be possible to avoid with the augmented reality proposed by you?
It's a very interesting question. If the system will prove to improve accuracy also for more complex procedures, then we can say that a first great benefit, a great mistake-free goal of the system is linked to the improvement in accuracy. Because sometimes, for example, you would be wanting, you want to resect a tumor using a certain boundaries, but the visualization through augmented reality allows you to respect these boundaries as you planned, but also having perfectly in your field of view the real anatomy. And so you won't be losing the connection between the virtual information, the planning, and the real anatomy. But I think that one big, say, benefit of this system could be what it gives you from the educational and from the training point of view. Because this kind of tools could allow surgeons, training surgeons, but also expert surgeons, to try the procedure, to test the procedure before surgery, having so the next day in the OR a much more clear view and consciousness of what they are doing. But also allows surgeons to train on, for example, on cadavers or on physical models to improve a specific technique, and of course this could be a benefit for errors, for mistakes, because a very well trained surgeon usually does less mistakes, makes less mistakes.
Thank you. No, there are no more questions, so I think this is the end of our webinar. I would ask the participants to switch on the camera and Giovanni to stop sharing the screen so we can say hello to each other. Thank you very much to the participants. Thank you very much to the speakers. And we are looking forward to the future of this wonderful technology. Thank you.
Thank you all very much.
Thank you very much. Take care.